So good afternoon, everyone. Today we're lucky to have Collin Politsch, who is a postdoc fellow in the machine learning department at CMU, supervised by Ryan Tibshirani. He received his joint PhD in stats and machine learning from CMU with his thesis titled Statistical Astrophysics from Extrasolar Planets to the Large-Scale Structure of the Universe, supervised by Larry Wasserman, Jesse Sawulski-Keeve, and Rupert Croft. His research interests include applications of statistical machine learning methods to problems in astrophysics, spatial-temporal data analysis, uncertainty quantification, and forecasting COVID-19. Without further ado, Collin, thanks again for coming, joining us virtually, and feel free to start whenever you're ready.
Thank you. I'm really excited to be here. Thank you all for having me. And I'm really excited to talk about this work today. As Simon just mentioned, more recently, during my postdoc, I work pretty much exclusively on forecasting COVID. I'm the head of forecasting development and evaluation in the machine learning department, the COVID-19 response team. But during my PhD work, I focused pretty much exclusively on the intersection of astrophysics, statistics, and machine learning. And in particular, this project that I'm going to talk about today has been, was the primary component of my thesis work at CMU. So let me just parse this, the title of this talk, because this is a little bit not statistically friendly. Three-dimensional cosmography here just means three-dimensional mapping the universe. High redshift universe just means the very distant universe, or equivalently the early universe, since the finite finite speed of light makes the two equivalent. And then using intergalactic absorption just means that I'm going to be using the absorption features in the spectra of very distant luminous objects. Okay, so my collaborators for all of this work, Larry Wasserman, Jesse, and Rupert, also known as my PhD advisors previously. So all of this work has been done with them. I'll briefly say, just as an overview of my thesis work, I've worked on various problems in astrophysics, and statistics is pretty much exclusively what I do. Is an astrostatistician, I guess, would be the best way to describe me. I'm not going to go through each of these in detail for sake of time, but for those who may also work at this interface, if you see anything here, I'm sure we could have interesting conversations or collaborations. But what I'm going to focus on today is the intergalactic medium, mapping the intergalactic medium via the Lyman alpha forest. We'll define these terms in the background section in the coming slides. All of these applications can be found in chapters 2 and 3 of my thesis, which will be released soon, as currently embargoed for a few more weeks or so. Also can be found in monthly notices of the Royal Astronomical Society, a couple of papers we published earlier this year. Okay, my slide transitions are a little bit glitchy, so I apologize for that. Okay, so first I spaced this talk into 3 different sections. The first section is background. I'll talk about the Lyman alpha forest, what it exactly is, the physical phenomenon where we're getting our data. A little background on that, the Sloan Digital Sky Survey, the sky survey that actually collected all the data that we're using. And then right up front, I'll give you a summary of the work, a high-level summary of the work, and a high-level summary of those results. And then I'll spend sections 2 and 3 actually getting into more of the statistical details and everything. So up front, there's not going to be too much statistics, but I promise that in sections 2 and 3, we'll get a little bit into more of the statistics. In particular, spatial modeling techniques is going to be the focus of the statistical content. Okay, so the Sloan Digital Sky Survey is the most prolific astronomical precision redshift survey to date. And so basically what it's done over the course of approximately the past 20 years is gather spectra for all of these galaxies that we see in this animation here. And so here we are at the middle of the local universe. And all of these pixels that we see around us are galaxies that the Sloan Digital Sky Survey has observed. When we get really close, we're able to observe a lot more. And so we can actually resolve the structure of the universe by looking at this point process distribution. We see this filamentary structure, we call it, the cosmic web. We call it a web because it's kind of looks like a spider web. And so at the nodes of this web, We call these galaxy protoclusters. They're groups of galaxies that evolve into galaxy clusters at more recent times in the universe. And then we have the filaments that are kind of just the stringy parts, and then the darker parts where galaxies are more diffuse are called cosmic voids. All of these things are of interest to studying the universe and constraining our understanding of the cosmological model. Okay, so that's the very local universe, but at higher redshifts, what we call it, is just another way of saying, astronomical way of saying high radial distances. We have quasars. So quasars are also galaxies, but they're galaxies that have that are very luminous because they have active supermassive black holes at their center, and so they're swallowing up all sorts of matter and therefore shining very brightly. And since they shine very brightly, we can see them from much, much farther away, almost all the way across the observable universe, in fact. And so in this work, what we've done is use these white objects and some of the yellow ones. And so these are high redshift, very, very distant quasars. And we analyze the spectra of them, in particular, the absorptions, pool them all together to make this map of the universe. What exactly we're mapping, I'll say in the next slide. Okay, so what I've just shown you is this point process distribution of galaxies that's been gathered by the Sloan Digital Sky Survey. And so they look at each of these points in this point process and they gather an electromagnetic spectrum for it. And so natural question is, what else can we learn about the matter distribution of the universe? Well, the matter distribution of the universe is pretty much can be broken down into these three components. We have the galaxies, the point process. We have the intergalactic medium, which is a diffuse intergalactic gas that envelops this point process distribution, all the galaxies, and actually gives rise to it through gravitational collapse. It pulls together and forms these galaxies. And then we have the dark matter distribution. All of these distributions trace each other very closely because of gravity. And the focus of this talk is going to be the intergalactic medium, is what we've mapped in our work. And so I'll say, again, the intergalactic medium is a highly diffuse gaseous medium that pervades the volume of intergalactic space. Intergalactic space constitutes overwhelmingly an overwhelming volume of the cosmos. And so even though it's so diffuse, it contains a majority of the baryonic matter in the universe. When I say baryonic matter, I just mean atoms from the stuff on the periodic table, not dark matter.
Colin, a quick question from Yue. So Yue, feel free to call out your question.
Mm-hmm.
Oh, sure. I also posted this in chat for others to read. If we chose a different center to be our local universe, would the structure look effectively similar to what's displayed here, or is there no way to actually know? Like if we centered ourselves around those like white galaxies around the outside, would we like centered there, would it still look very similar around us?
Yes, it's certainly believed to be so by Albert Einstein, and general relativity is the cosmological principle that no matter where you are, the universe looks pretty much the same as you look out from your own observable position.
Thanks.
Okay, and so this is just a very small cubic simulated universe by Renyu Chen and Jeremiah Ostrecker. Okay, so how do we actually know that the intergalactic medium exists? And where do we, and therefore, where do we get our data from? Where does the data come from? There's this broad kind of field, this set of tools, I'll say, called absorption spectroscopy, which some of you may be familiar with, even not in an astronomical context. It's stuff that we do here on Earth as well. And so what we do in order to actually get these measurements is absorption spectroscopy with quasar backlights. And so those really, really bright, distant quasars that I pointed to earlier, we use absorption spectroscopy, which is just a set of spectroscopic techniques that measure the absorption of light as a function of wavelength due to its interaction with some medium. And so in particular, the medium in this case is the intergalactic medium. So that gaseous, highly diffuse medium that's in between all the galaxies in that seemingly dark volume of intergalactic space. And so here we're looking up in the sky. We see this very, very faint light source here. Zoom in a little bit. It's not exactly clear a priori just from photometry what exactly that is, but you gather a spectrum for it. And this is kind of a whole other problem in astronomy, is that once you gather a spectrum, you can classify what exactly that object is and how far away it is. And so based on this spectrum, we can say with high confidence, I'm just taking this for granted right now, that this is a quasar at redshift 2.39. So again, redshift is just an astronomical coordinate. It just means it's at a particular radial distance. This is actually a project that Larry Wasserman and I, one of my PhD advisors, are currently working on, but I'm just going to glance over this for now, that we take this for granted, that given a spectrum, we can determine that what type of object we're looking at, a quasar, and how far away it is. Okay, so zooming in a little bit, let me say just for a sec, I have all these absorption emission lines marked in this spectrum here. What we're interested for the purposes of this work is the Lyman alpha spectral line here. And so Lyman alpha traces the absorptions of electrically neutral hydrogen in the intergalactic medium, which is the most abundant atomic element in the intergalactic medium. And so we're kind of using this as our proxy for the total matter distribution in the intergalactic medium. And so you see all these wiggles here, what we call blueward, which of the Lyman alpha spectral line, blueward just means at shorter wavelengths. So it gets really wiggly here. And these wiggles are because it's transecting this hydrogen gas in the intergalactic medium as it's passing through intergalactic space in between the quasar and us here on Earth. I'll have another slide here to kind of hammer this point home, because it's not easy to grasp the first time. So zooming in here on this simulated version of this spectrum here, here's the Lyman alpha transition again. This orange dashed line that I'm showing you here is called the quasar continuum radiation. And so it's this very smooth spectrum that this is what the quasar light looked like when it first left the quasar. And then it travels through intergalactic space, and the light at this wavelength begins hitting all these hydrogen atoms in intergalactic space, and you get these absorptions that cause these decrements from the continuum. So this is intergalactic hydrogen absorbing the light. So effectively what you can do, you can kind of telegraph where I'm going here with the statistical problem, is that if you can infer the continuum, then you can kind of invert these absorptions into a one-dimensional map of the universe along this line of sight, based on how much gas, based on how much light is being absorbed by the intervening gas. Okay, so let's kind of get a look of how this physical process plays out in pseudo real time. On the left here, we have a quasar shining very brightly from, let's say, all the way across the universe, traveling along a line of sight to us, and we're somewhere over here on Earth, and then there's all this intergalactic gas intervening, and we'll see what happens to the spectrum of the quasar as it passes through this. And I'll just point out right here as Lyman alpha, the spectral line that we're interested in. There's a lot of other stuff going on here, but we can just ignore all of this, and let's also ignore this. Just focus on Lyman alpha. Okay, so slow it down. The light's passing through intergalactic space. It's going through these dense hydrogen patches. It's this continuous distribution of hydrogen, so it's not, used to be thought to be kind of clouds, but it's really a continuous distribution. And as it passes through these more dense regions, you get the deeper dips. You get the deeper dips in the continuum. And so that's basically the physical process here. And then the goal is going to be to invert and get that relative distribution of hydrogen. Okay, so I'm showing you basically just the sampling design, the sky survey that we're dealing with, in particular the Baryon Oscillation Spectroscopic Survey. It was a sub-survey that operated within the Sloan Digital Sky Survey, that 3D map animation that I showed you earlier. The Baryon Oscillation Spectroscopic Survey wrapped up observations in 2014. The data is publicly available. That's why we used it to create our map here. The more recent data isn't quite publicly available yet. So what I'm showing you here is a two-dimensional projection of all of the BOSS, Baryon Oscillation Spectroscopic Survey, quasars and galaxies. Actually, I apologize. Let me back up one sec. There's one more important physical phenomenon that I need to draw attention to. The reason that this spectrum, as this light is traveling through space, this spectrum is shifting to the right to longer wavelengths, is because of what's called cosmological redshift. The universe is expanding. And so the space, all of the space around us, all of these objects are getting farther and farther away. And so as this light is traveling through space, the space itself is getting farther away, which is causing a Doppler shift on the light, which is actually really helpful and makes this problem possible. Otherwise, we would just get, if the universe was fixed, we would just get a single absorption line here and the spectrum would remain stagnant. But because of the Doppler shift, we get all these absorptions over a series of wavelengths. Okay, so we use the entirety of the BOSS catalog of Lyman alpha quasars in order to make this map of the intergalactic medium that we've done. One of the consequences of the fact that the Lyman alpha spectral line lies in the ultraviolet wavelength range is that in tandem with the fact that ultraviolet wavelengths are absorbed by Earth's atmosphere, is that these wavelengths have to be Doppler shifted a certain amount before they actually become transparent. Our atmosphere becomes transparent to them, which again, we're very happy for. It keeps us safe here on Earth. But these Lyman alpha forests have to be stretched quite a bit before they can be observed by ground-based spectrographs. And so effectively, it's around redshift 2 at these more distant regions, ironically enough, is where we can make this map. We can't make the map at the closer ones yet without space-based telescopes focusing on Lyman alpha observations. So we use all these Lyman alpha quasars out here at the higher redshifts. And then here's a nice animation I'm showing you on the right, made by some graphic designers at the Sloan Digital Sky Survey. They're showing you exactly what I'm going to show you that we've mapped in this work. The intergalactic medium is this smooth gas at these higher redshifts, these more distant regions. Here's all the galaxies in the closer, more local universe, and then there's the gas out here higher, and then the observable limit, of course, being the cosmic microwave background radiation, very famous two-dimensional all-sky map of the universe. So in total here, we have approximately 160,000 usable Lyman alpha quasar spectra that we pool together to make this full map of the universe. So as promised, I'm going to give you a very high-level summary of the work, the steps that we took, and then I'll give you a high-level summary of the results before diving into some of the details. So again, what I'm showing you here is what I call the Lyman alpha quasar. So Lyman alpha quasars just being the quasars that are far enough away that their spectra are Doppler shifted so that we can see them from Earth. And so this is where we make our map of the universe at these higher redshifts. So step one is to take each one of these quasars, each one of these quasar spectra, and infer the relative density of the intergalactic medium along the one-dimensional quasar line of sight. So that's what I'm showing you on the right here. Is for each of these given pixels or voxels, we make a one-dimensional map along the line of sight. So we kind of have this porcupine design on the right here, where we've taken all the 160,000 Lyman alpha quasar spectra and made them into 160,000 one-dimensional maps of the intergalactic medium. Step two is to pool all these sight lines, to pool all the one-dimensional maps to reconstruct a full three-dimensional large-scale structure map of the intergalactic medium. Step three, we're statisticians, we're very statistically rigorous. So step three is to quantify the total statistical uncertainty all the way through this modeling pipeline, all the way through to the final stage of three-dimensional reconstruction. And then step four, for now, at least in our past and current work to this point, is to use this uncertainty quantification framework, this total statistical uncertainty, to identify statistically significant candidates for interesting objects being like galaxy protoclusters and cosmic voids that correspond respectively to statistically significant overdensities in the universe, in the intergalactic medium, and statistically significant underdensities. And so remember, galaxy protoclusters are just those nodes, those nodes of the cosmic web that I pointed out in that video earlier, and then the voids are those, the more empty spaces, the black regions. Okay, summary of results. So the takeaway is that this is the largest volume, large-scale structure map of the universe to date. This is definitely the primary component of my thesis. We worked on this very hard for very many years. And took a lot of work, and this is just this is a look at it. So at these lower radial distances here, lower redshifts, these are the boss galaxies, and these higher redshifts, this continuous map here, this is our map of the intergalactic medium. On the left here, I'm showing you an actual three-dimensional subset of it, approximately 1/1000th of the volume of the map. And you kind of get an idea, the depth of the map here. I'll give you some logistical things here. Some of these are a little bit astrophysically technical. These are just measurements, and so it's 154 cubic gigaparsecs. And so, yes, by far the largest volume map, large-scale structure map of the universe to date. It covers approximately 10,332 square degrees of the sky, and so that just means it covers approximately a quarter of the sky. Has about 3 times more coverage up here in what's called the northern galactic cap. It's like the astronomy version of the northern hemisphere, and then about 1/4 of that is down here in the southern galactic cap. Redshift range is just the depth here, 1.98 to 3.15. And then using that uncertainty quantification framework, we've identified approximately 180,000 high significance, so at least to 3 sigma significance candidates for galaxy protoclusters and cosmic voids, approximately 180,000 of each of those types of objects. As you can imagine, and anybody who does spatial modeling knows this well, that it's a very expensive, computationally expensive endeavor, and indeed it was. It cost us approximately 3 million distributed CPU hours, approximately 342 distributed CPU years. Oops. And so this is not multi-threaded or multi-core. This is fully distributed, distributed over many, many machines, each machine being configured with about 200 gigabytes of RAM, and that each of those machines with 200 gigabytes of RAM is each of these units of time. So I'll show you one more little cross section here of the map. So I'm showing you the all sky view, and so this is, this covers about 25% of the sky. Over here is the northern hemisphere, the northern galactic cap. Over here is the southern galactic cap, and then looking at this, so this variable that I'm plotting is Lyman alpha flux contrast, which I'll define in a moment, but basically the takeaway is that these red regions are overdensities in the universe and blue regions are underdensities in the universe. And so not only do we model this entire continuous distribution, but using the uncertainty quantification, we can say things like, probably this dark red region, it may be a statistically significant candidate for a galaxy protocluster. And then conversely, you see these blue regions here, and that might be a statistically significant candidate for a cosmic void.
Collin, quick question.
Yeah.
So you mentioned that in this case, you were using this sort of spectrometry data to do this sort of map reconstruction. Now, one can imagine that you can use other types of maybe certain physical models on how the light sort of shifts around. There are sort of established models which can guide this sort of reconstruction as well. So do you make use of any of these physical models, or is this purely data driven?
This is purely data driven. And so there are certain things, I haven't even gotten into the statistical modeling yet. And so you're asking about the data, am I right? Or you're asking
right. So there are models that I can sort of simulate, at least, at least the core problem, where given a map, I can sort of simulate how the light sort of goes through these sort of intergalactic sort of clouds and goes to Earth, right? So the question is, do you integrate, or is there any way of perhaps integrating such models into this type of procedure to perhaps improve the sort of reconstruction?
Perhaps it might be possible. And so we were talking a little bit offline that I do take a fully data-driven approach here, and there are many reasons that we decided to do that. But I will say that there are a number of more probabilistic approaches in the literature for these spatial modeling, and I will strongly argue, I'll die on the hill, that they're making bad probabilistic assumptions, and so I don't support the probabilistic assumptions in this case, because the spatial process here is just so complex. The universe is a very, very complex multi-scale spatial process, and there's no way that you can input that into a prior. And so people do things like assume that all of this is just a Gaussian random field and that there's white noise errors and stuff like that. And it's just a completely misspecified model. And so I think everything after that, the uncertainty quantification, the hyperparameter optimization, maximum likelihood, I think it's all just like, I think it's all out the window at that point is what I would argue, or politely argue to those people. So yeah, we do take a very data-driven approach. And so you'll see that in the coming sections.
Great, thanks.
Mm-hmm. Okay, so the main focus of this talk is on the three-dimensional mapping of the intergalactic medium, of course, but one-dimensional mapping is an essential stepping stone. We argue that you have to be able to do the one-dimensional problem well before you can move on to the three-dimensional problem. So I'll quickly discuss our work on the one-dimensional problem, which is already published work. And so there's those couple papers and monthly notices that you can refer to for this work. I'm going to kind of go quickly over that and spend most of the time on the three-dimensional problem. And I'm already glancing to make sure I keep track of time here. So as promised here, we'll finally start to get into a statistical model. And so we have these quasars here passing through a foreground intergalactic medium. The assumption is that we're going to observe some flux here, so some intensity of the light per unit time per unit surface area, and there's going to be some signal in there, and there's going to be some noise. And then this flux can factor into the continuum of the quasar. So that orange dashed line that I drew your attention to earlier, times some transmission probability, or it's called flux transmission, transmitted flux, many different names. But yeah, effectively you can think of it as the probability that any given photon makes it through the gas at that particular point along the line of sight. And then again, we're going to factor this transmission probability into this term here, where we have an average transmission probability over the full sky, and then we have this 1 plus delta F here, where delta F is our Lyman alpha flux contrast. This is zero mean random variable that gives you the fluctuations about the mean cosmological density. And so this is the response variable, the spatial variable of interest in this problem. So just to define it explicitly here, it's just the kind of fractional differences about the average cosmological flux absorption. So transmitted probability minus average transmitted probability divided by average transmitted probability. So I'm not going to get into the reasoning here. Again, this is stuff that's in our published work, but we propose this one-dimensional estimator along each of these quasar lines of sight that we show and we argue does pretty well. And so we get a denoised, a one-dimensional denoised version of this spectrum first. So you just take the observational model, this black line here plus some noise. You denoise it first with some smoother that I'll say more about in a second. And then M, you let M be the continuum radiation. So this very smooth orange function times the transmission probability, which effectively makes it a very smooth mean function, which is much easier to estimate than a very smooth maximum function, which is effectively what the continuum is. So you estimate that with another non-parametric smoother, and then define this estimator as such, and we show that that's a pretty good state-of-the-art estimator. And so I'm showing you the results here effectively. This is a simulated spectrum, and so in orange we have the denoised version of the observational model, and in particular this F0 hat that we're using is called trend filtering. It's a pretty new non-parametric, non-linear non-parametric smoother from this Tibshirani Annals of Statistics paper in 2014 that we're quite keen on. And so in particular, we went the non-linear route here because these abrupt dips in the Lyman alpha forest it's suboptimal to use a linear smoother like local polynomial or smoothing splines, coronal regression, anything like that here is suboptimal because it will over smooth these deeper dips. And so we go the non-linear route here, and then we use a very, very smooth low S here where we're optimizing the bandwidth over a large set of simulated spectra. And then as defined here, the estimator, you can see in this particular case, it's tracking the truth of the simulated example pretty well. There's the Tibshirani paper, and then a couple more trend filtering papers that we wrote earlier this year. I might start to pick up a little bit, so I apologize because we're already at 30 minutes. The question, of course, is uncertainty quantification, because I keep talking about all this statistical uncertainty and we're statisticians. And so not only do we want this point estimate map, one-dimensional map of the intergalactic medium, we want uncertainty quantification. So we propose this parametric bootstrap procedure where you take the trend filtering estimator and you construct each bootstrap sample by adding some Gaussian noise to it. Gaussian is actually quite a reasonable assumption in this case. The spectroscopic pipeline from the Sloan Digital Sky surveys pretty well vetted to the point that I'm a skeptical statistician and I do feel pretty good about this Gaussian assumption. So I'm not too worried about that. And nicely enough, they do provide us pretty good estimates of these measurement variances. So we construct each bootstrap sample that way, and then we come up with an estimate for the Lyman alpha flux contrast along the line of sight, exactly the same way as the point estimate. So define it exactly the same way as this fractional transmission probability, and then construct these point-wise variability bands by taking the percentiles of the bootstrap distribution. Okay, so that allows us to not only provide this one-dimensional point estimate map of the universe along each of these lines of sight, but also provide these variability bands so that we can see things like this, these deep dips, and actually say, okay, this is in this case a 95% variability band. We can say, okay, with confidence, we're pretty sure that this is a significant overdensity in the universe. So this is something like either the light is passing through a galaxy protocluster or it's passing over a filament in the cosmic web. Something that's overdense is there. Okay, now three-dimensional mapping the intergalactic medium. So I have about 20 minutes to do this, and this is the main point of my talk. This is a problem that's colloquially known as Lyman alpha forest tomography. And so the idea here is to take all of these one-dimensional maps, or equivalently take all of these, this dense set of quasar spectra observed on the sky. I'm showing you three-dimensional rendering here. And so first we make the one-dimensional maps, but then take all the one-dimensional maps and reconstruct a large-scale structure map of the intergalactic medium from the one-dimensional maps. So obviously we're going to have some limitations here, because as I've harped on many times already, the universe has structure on many scales, all the way from the very largest galaxy superclusters down to you and me. And so in order to make a three-dimensional map here, we're only feasibly going to be able to reconstruct the three-dimensional large-scale structure down to the approximately average transverse sight line separation. We can't recover any three-dimensional structures where we just simply don't have the line of sight density. Okay, so now actually getting into the objectives / essentials that we argue make up the problem of Lyman alpha forest tomography. In the literature, so this is something that's been explored. It's been for 20 years or so. It started with simulated examples and everything. And basically, as far as the literature goes, the problem is basically just posed as reconstruct a three-dimensional map, large-scale structure map from a dense collection of one-dimensional maps. We go quite a bit further in our work. We argue that there's a lot more that we should be doing. That we should be optimizing the map to be predictive of structure in between sight lines. So as I already said a little bit in some of the Q&A, most of the literature out there makes some probabilistic assumptions that I'm really not on board with, my advisors as well. And so we take the approach that what you should be doing is be very data-driven about this. We want to reconstruct a map so that it's optimally predictive of held out of sample structure in between the sight lines. And we want to be doing this very, very non-parametrically. Multi-resolution, and so again, as I keep mentioning, the universe has many, many scales of resolution. So should our spatial statistical models that we use to model it. And again, this is something that's very novel in this sense. People usually don't take into account multi-scale spatial dependence in cosmography. Uncertainty quantification. This is another area that has been very, very lacking in the cosmographical literature and Lyman alpha forest tomography in particular. And so, but yes, we're statisticians, and so we're very, very careful about these things, tracking all of the statistical uncertainty in the reconstructed three-dimensional map, all the way from like the photon noise observed in the flux of the quasar spectrum, all the way through to the modeling pipeline, finally to the final stage of three-dimensional reconstruction. And then our final one here. So the primary reason that a map like this hasn't been made before, only very, very small volume maps have been made before on usually simulated data sets, and in some cases, very, very small patches of the sky, like less than the sky coverage of the moon, like smaller than that, simply because it's spatial modeling. It's an incredibly computationally expensive endeavor. And so this was a very non-trivial component of the work. And so we were able to actually circumvent or make this happen by using these two components in tandem, enforcing sparsity and the key matrices for the computations of the spatial model, and then also distributed computing. And so we come up with a distributed approximation of the spatial model that allows us to then partition it, the problem horizontally over many, many machines. And then, as I just mentioned earlier, the transverse separation of these sight lines being kind of a key feature of this problem. This is the mean transverse sightline separation as a function of the radial distance. So as you can see here, as you get farther and farther away from Earth, the sightline separation gets coarser and coarser and coarser. Of course, that's going to happen just naturally geometrically, but the primary reason it happens is because these quasars get fainter and fainter and fainter and harder to observe. And so that's something that we're going to have to take into account in our spatial modeling, is that the large scale structure on which we're able to feasibly recover becomes much, much coarser as you get farther and farther from Earth. Okay, so the spatial model that we actually ended up using, we went through many, and
Sorry, Collin, a quick question, just to interrupt you. UA has a question.
Hey, sorry, it's me again. I was wondering if there's any way to physically verify predictions between sightlines.
Physically verify, yeah, so the way, that's a good question. You're actually getting ahead of me a little bit. And so the way that we do that is with cross-validation, where you actually hold out entire sightlines. And so you hold out entire quasars, and and then you use those one-dimensional maps that you didn't use to verify to validate your model.
Great, thank you.
Okay, so through the years, and especially the early years of my PhD at CMU, I spent all kinds of time trying to figure out what the best spatial model, what the best way to approach this problem of mapping the intergalactic medium. And that's detailed in my thesis. So I'm just going to take for granted now that this is the spatial model that we eventually settled on. So we call it a multi-resolution spatial kernel ridge regression. So it's just summed up by this cost functional here. It can be pretty concisely stated. This first term here is just a weighted sum of squared errors, where the delta F hat here is the aggregated vector of one-dimensional maps. And I have a hat because we've already done that first modeling step of reconstructing the one-dimensional maps. Phi is a regression matrix built up from a multi-resolution set of compactly supported radial basis functions. And then beta is just the coefficient vector of each of those. W is a weighting matrix that's naturally, it's kind of your basic inverse weighting scheme. A little bit more complicated than just simply inverse weighting with respect to measurement errors. We're doing something a little bit more because there's also small scale structure that you want to inverse weight as well, but I won't get into that. And then second term here is our spatial penalty. And so this is a generalized ridge penalty, as you'll recognize. So just traditional ridge penalty, but we have this generalized ridge matrix here. That I'll describe in more detail in a second. And the idea is that once you get this these optimal beta coefficients of this multi-resolution basis, then you simply just plug it into this basis expansion, and then you have your delta F hat L here, L for large scale structure. And that's the point estimate of the map. And so I'm showing you an example here. Here's just a 3-level example of the multi-resolution basis. In particular here, we're using a Wendland basis, which is just built up from compactly supported Wendland polynomials. And then here I'm showing you an example of the spatial penalty. And so this generalized ridge penalty here, again, with this 3-level example, here's a 2-dimensional example showing you that this spatial smoothness that is being encouraged in this kernel ridge estimator. So we have a very coarse scale in this case, a slightly intermediate scale, and then a small scale. Okay, so back to this kind of mysterious generalized ridge penalty matrix. What exactly is this that we do? So we build it up as this block diagonal penalty matrix, where the number of elements in this block diagonal is equal to the number of levels of resolution in the spatial kernel ridge regression. And then each of these blocks in the matrix is this sum of a spatial penalty. And so I'll say we use first order fusion here. And so this is encouraging spatial smoothness among neighboring basis coefficients. And so basis coefficients that are close to one another are encouraged to be similar, thus imposing spatial smoothness. And then we have an identity matrix here, and we have 2, which just corresponds to a pure ridge shrinkage. And then we have 2 hyperparameters in each of these blocks. And so the alphas dictate the range of the spatial dependence, and then the gammas dictate the total contribution of that level of resolution to the total model. And the reason this is 6 is because this is a 3-dimensional problem. So a 3-dimensional lattice, each of these nodes has 6 first order neighbors. And so 6 minus 6 nodes is being penalized to 0. So the basis coefficients are being encouraged to be similar. For sake of time, I could walk through this and explain it exactly the mechanics a little bit, but I'm going to skip ahead. Okay, so I'm going to talk about distributed computing, as I mentioned. Back to this cost functional again, this is strictly convex and differentiable everywhere as a ridge regression, and so it has a closed form solution. We have phi being the regression matrix of compactly supported radial basis functions, so it's very sparse. W is diagonal, phi again, very sparse, so phi transpose W phi is very, very sparse. D is that first order fusion matrix, and so just 6s and -1s and then 0s everywhere else. So D transpose D is a second order difference matrix, and so it's also very, very sparse. So altogether, this Gram matrix is very, very sparse, and so we can solve this linear system very, very efficiently via sparse Koleski decomposition. Does that mean that this is easy computationally? Absolutely not, because we're dealing with a truly massive spatial problem here. And so we have aggregating all these one-dimensional maps, the pixels that we use, like recall that I said 160,000 one-dimensional maps. In total, the number of pixels is 72 million, and mapping the intergalactic medium at or around the transverse sightline separation means using 40 to 50 million radial basis functions. So that's P, 40 to 50 million. So this is a truly massive spatial problem. So we construct, we absolutely have to construct a distributed approximation here. And so the way to kind of, the intuition here is that this spatial penalty, you can think of this, just take this to be the largest, the coarsest scale of resolution. Beyond a certain pairwise separation, the spatial smoothness of this estimator becomes trivial. It's never exactly 0, which is just an artifact of the ridge regression. It's never exactly 0, but after a certain distance, it's effectively, it's trivial. And so we can partition this full 47 cubic gigaparsec volume into a bunch of smaller subsets, and then construct local estimators, local maps of the intergalactic medium. So here's a local set of basis functions constructed, or a local set of basis coefficients using a local set of radial basis functions and a local penalty. And then here's our local map. And then once we've computed all the local maps, we piece them all together in a piecewise fashion as so. And so this is this delta F hat superscript L parallel is our distributed approximation of all of these, I think about 1,700 submaps pieced together into the full map of the intergalactic medium. Okay, so I'm running a little bit low on time. So let's see, model validation here. We have all kinds of hyperparameters here that I've introduced. And so as I already kind of conveniently alluded to, we do not exactly cross-validation, just data splitting, because again, this is all very computationally expensive and I wanted to finish my PhD at some point. So just a data split, 8515, and we hold out entire quasars. So it's not just random pixel train validation, it's holding out the whole quasar line of sight. This is a little technical step here that I'm gonna skip over. And then of course, what validation loss function should we be using? In this case, we use Kendall tau ranking distance. There's some intuition that I could provide in Q&A about why we do that, but I'm going to skip over it for now. But Kendall tau, this looks a little bit complex, but it's easier to understand via its kind of colloquial alias, the bubble sort distance. And so we just take the validation set predictions for a given hyperparameter vector given by the coronal ridge regression, and then see how many bubble sort swaps it takes to get to the held out validation one-dimensional maps. And so that's kind of the intuition there, is that we're trying to reconstruct an optimal relative density distribution. And so we want it to be as close to that density as possible. And these vectors are just discrete evaluations of a density field.
Question in the chat from Michelle, I think.
Mm-hmm.
Question in the chat from Michelle. So feel free to say it on the call.
Yeah, sorry. Referring to a slide that I saw earlier, when you're using reach penalty, that makes me think of a probabilistic interpretation as a Gaussian process prior, like, yes, even here in the cost functional. So I was thinking, like you were mentioning how you did not like that, but that's literally what I would think looking at that.
Yeah, so you're absolutely right. So there is an analog in penalized regression, and there's almost always, to my knowledge, an analog to a Bayesian problem. The difference here, and so if you just, this is the solution right here, this beta hat is the solution to the posterior mean of a Gaussian process regression. But the distinction here between the frequentist and the Bayesian approach comes in the hyperparameter optimization and the uncertainty quantification. And so the hyperparameter optimization here being simply that we're optimizing all of the hyperparameters to be predictive of held out of sample observations. And so that's the first difference. And then the uncertainty quantification, we use a parametric bootstrap procedure. We're not doing some sort of posterior sampling or anything like that.
Okay, thanks.
Mm-hmm.
Great. And another question from UNC.
Hi, this is Yuan. I'm just wondering, can you explain a bit more about the basis function that they're being used? Like px 50 million sounds like a lot of basis functions. Yeah.
Yeah, it is. It's quite a lot. So are you more curious about the number or the type of basis function?
Yeah. How you get to the 50 million, or is that something that you really think it's necessary to include all these bases in the model, or yeah, I'm just curious.
It is. So in order to actually map this volume of the universe at the resolution of the transverse sightline separation, so you just lay out all of these basis functions at that scale, and then you can decide on how many coarser levels of resolution you want to add. But most of the basis functions are in that finest scale of that finest level, and that produces that number. It's not really, I mean, it's dictated simply by the vastness of the volume of the space that we're mapping.
Great, thanks.
Okay, so yeah, given this bubble sort distance, this Kendall tau ranking distance loss function, we just simply search over a large number of combinations of this hyperparameter vector that minimize this Kendall tau raking distance, and then recall this phenomenon that I mentioned earlier about this kind of design heterogeneity in the number of observations we have. And so kernel ridge regression is a little bit spatially adaptive, meaning that if you have a dense, in areas where you have a lot of observations, the kernel ridge regression estimator will become a little bit wigglier. It'll become a little bit higher resolution. When observations are sparse, it'll become a little bit smoother. But this is pretty severe design heterogeneity. And so in order to provide an extra boost of spatial adaptivity here, or design adaptivity, I should say, we optimize the hyperparameter vector separately in each of these 3 radial bins. Okay, so now we have this closed form distributed solution for our very large map of the universe. So that gives us back this, what I showed you right up front here. Here's a 2-dimensional cross section of the map at one particular radial distance from Earth. Yeah, so here we are again with red being the overdensities in the universe, blue being the underdensities in the universe. And then I'll show you here some various radial distances as I quickly go. Yeah, I think I'm okay on time. As I mentioned earlier, with the design heterogeneity being basically almost monotonic as a function of radial distance, you see here the resolution of the map as expected at these lower redshifts, these lower radial distances. It's a much higher resolution reconstruction. And then you get out to the higher redshifts, the greater distances, and it's lower resolution. Again, completely as expected. Okay, but of course, the question, statistically, and it didn't take super long. Halfway through my PhD, I had a point estimate, but the more difficult question was the uncertainty quantification. And so we want to know what's real here. And so basically, this is an extension of the one-dimensional uncertainty quantification, the parametric bootstrap that I went through earlier, is that for each of these approximately 160,000 quasars, we do a parametric bootstrap starting at the observational data generating process. We construct a bootstrap sample of each of these Lyman alpha forests. And then for each of these quasar spectra, we construct the one-dimensional map, just as we did before. So these first 3 steps are literally just exactly what I showed you in the one-dimensional problem. And then the additional step here is that you just do the entire 3-dimensional spatial problem again. So you do that full distributed 1700 submaps pieced together all over again with a new bootstrap set of quasars. Okay, so and so we did that. We produced 50 bootstrap reconstructions of the full 3-dimensional map of the intergalactic medium. Ideally, I would have liked to do more than 50, but again, this all took a very long time. So we called 50 sufficient. And a kind of nice, I will say unexpected, but pleasant surprise here was that this bootstrap distribution comes out to be extremely close to Gaussian, which we'd like, because then we can just look at this. This is a cross section of the standard error field here. And so for much of the science here, the uncertainty quantification results, you can just save the standard errors. We're releasing all of this in a SQL database, so you can just save the standard errors as a column instead of saving all 50 bootstrap reconstructions. And in my last slide, I'll tell you just how large this data product is. And so it's kind of essential to be able to just compress it as much as possible. Okay, so kind of our first order science now that we've done with this point estimate and this statistical uncertainty quantification framework that we've provided with the map of the universe is cataloging these candidates for galaxy protoclusters and voids. And so we define statistically significant candidates for galaxy protoclusters to correspond to statistically significant overdensities in the intergalactic medium, where overdensities are defined as these level sets here, where we have this distributed reconstruction of the intergalactic medium. And when it's negative, when it's at least in standard errors away from zero, below zero with respect to that bootstrap sampling distribution, then that's a statistically significant overdensity at n sigma. And then conversely, the same for statistically significant candidates for voids. They're underdensities that are at least n standard errors above zero with respect to the bootstrap sampling distribution of the three-dimensional spatial model. So what that allows us to do, this is what I've already shown you before, is just a small piece of our three-dimensional map of the universe. So not only can we provide this, the three-dimensional continuous density field, is we can also provide this. We can pick out all of these interesting objects in here and say, hey, here are all these things. We're giving you this catalog, and we're at least, 3, 4, 5, 6, 7, 8 sigma sure that they're there, which the cosmologists really like. And you can use these things for various types of science. The next kind of future steps, we're interested in studying the distribution of these things in order to constrain the cosmological model. So, okay, I'm showing you, as I have just a couple minutes, I'll just show you quickly. I'm zooming out here for a second. I'm showing you another cross section, and I'm showing you these statistically significant structures that we've identified at one particular radial distance, red being protocluster candidates, blue being void candidates. And altogether, at least there's this kind of a hierarchical catalog here of significant structures. And so at 3 sigma, obviously you're going to get many more significant structures than at 8 sigma. At 3 sigma, about 180,000 of each of the types of structures. And then even all the way out to 8 sigma, around 20,000 very significant structures. And I should say, I'd be remiss if I didn't say that this is all very novel. Up to this point in time, these types of structures at these distances out in the universe, we've only observed on the order of a couple hundred. And so this is a significant orders of magnitude advance in this area. Okay, so this last slide basically just says, data products, and that we value open science and everything. We want everybody to use our data products here. So everything's going to be released on the Stat Department webpage at Carnegie Mellon at this link, powered by the Pittsburgh supercomputer. So there will be a SQL database that's currently being built right now, and at the end of the day, it's going to be approximately 30 terabytes. And so again, that's just including the spatial coordinates and the point estimate map and the standard errors. You can imagine how large it would be if we included all 50 bootstrap reconstructions, and we can't afford to put that out there. And so this is down to a 1 cubic megaparsec voxel resolution that people can just query whatever part of the universe they're interested in, cross-correlate it with whatever objects they're studying out there, galaxies, anything. Downloadable HealPix sky maps. So those are just the 2-dimensional sky maps that I've been showing you at all these different radial distances. And then all these catalogs that I've been talking about, candidates for galaxy protoclusters and voids for the whole community to study and do their science. Here's just some references, including a number of relevant papers for my PhD. These 2, 3, 4 papers here are all published. Everything that I talked about today is primarily this first one here, which is currently, like I said earlier, approved as inquiry at Nature, and so that's why everything's currently embargoed. We're just finishing up and submitting that very soon.
Excellent. Well,
and
thank you, Collin, for the interesting talk. Yeah. So I think Yue had a couple of questions. So Yue, feel free to ask them.
Sure, sorry, it's always me asking questions. First is that, like, for any given point in space, you can ask the question, are we in an overdensity or underdensity? Does this answer depend on the scale that you examine it on? So, like, if there are differences in, like, local voidness, can a point be classified in a void, but even on a finer scale, that's actually an overdensity? And then somewhat related is in thinking of the multiple scales that you're making predictions on in terms of your basis functions. When you're determining the best set of hyperparameters, especially for the penalties, did you find that your map was driven by reducing error in some sort over larger scales or smaller scales?
Okay, so the first part of that question, you're absolutely right with your intuition, is that everything's a matter of scale, and so in your smoothing scale and everything. And so our smoothing scale for this particular map is assumed to be approximately the scale of the transverse sightline separation. And so everything's defined according to that smoothing scale.
Oh, got it.
But of course, overdensities and underdensities in the universe go down to every scale of the universe. As I mentioned, like you and me, I'm an overdensity in the universe. And so second part of that question, I'm sorry, could you remind me the hyperparameters and everything? What was it? The spatial penalty.
Yeah,
I'm
like,
sorry,
did you find that your model placed more weight in terms of like making sure that larger scale or smaller scale fluctuations were better taken care of in some sense?
So we did find multi-scale dependence to be very important. And so multi-scale was very important. Small scale dependence, so around the transverse sightline separation, is the most important. And actually, in fact, most of the variation in the universe, which I know this based on, well, the one-dimensional problem will tell you this because you have higher resolution observations, and then also simulations of the universe. Most of the structure, most of the wiggliness in the density distribution of the universe is at smaller scales than are currently available at the transverse sightline separation. But relatively speaking, yeah, the smallest level of our three-dimensional model being at the transverse sightline separation, that is the most important. But at the same time, adding those larger scale levels of resolution are better than just simply having the one smaller scale.
Thanks. It's also, are we in a void?
Yeah, I was wondering what you were asking about that. Anyways, any other questions from the audience here, particularly questions from students? Okay, well, I have a quick question here, and this sort of relates back to my earlier question on, are there any sources of other types of data, perhaps from physical models that we can do? So in terms of the uncertainties that you get out, right? If you go back a couple of slides, I think on slide 25, or where you had uncertainty maps. Yeah, these maps. Are these standard errors, at least in terms of the literature, are these pretty large or pretty small?
There's not really physical literature on this. This is purely related to like the observational noise and limitations and systematic effects and everything, the spectroscopic pipeline. And so as our measurement instruments get better and everything, and the next generation sky survey being DESI just starting, and as we get more and more quasars and stuff, we'll see these standard errors shrink.
Sure, but another way of sort of perhaps shrinking these errors, because I mean, the reason why you want to shrink them essentially is that, if you go to the next slide, 25, right, you have how these things are then sort of picking out different clusters that you're interested in observing, right? And I would imagine that at least the physical models that would be governing this type of phenomena, of course, it's much more large scale, right? But I would imagine some of the physics here, under some sort of simplified sort of physical model, might be able to capture what's going on and might be sort of, can perhaps be simulated on a computer. So of course, one can argue that, these models might not be as accurate, right? There might be sort of unknown physics that were not captured. And so if we simulate those and integrate them in the model, that can cause certain biases, right? But, maybe like, would there be any sort of advantages in sort of integrating some of these models, or are there sort of inherent limitations for that?
So yeah, I have thought about the physics approach, and I've talked to people that work on this same type of problem, but come from the physics background, and so naturally they take the more physics-based approaches and everything. And so yeah, I guess my two answers usually are, I guess, like I already said, being that the physics is incredibly complicated. And so any physical models that I've seen used out there are objectively so misspecified. And so that's problem number one. And then number two.
Yeah, sorry, just quick follow up on that term, misspecified. So it's more like it's missing certain physics, or is it like miscalibrated? You don't know the certain parameters in the models?
So it's missing small scale physics.
I see, okay, got it.
Yeah. And then part two, I might have mentioned earlier, just being the fact that we want this, and it's very appealing as we have presented it to cosmologists, as this is a data-driven map of the universe based on observations, that now this can actually be used as a pretty, confident test of the cosmological model. Instead of using the cosmological model to produce the map, we can now use the observations, the statistical optimized reconstruction to now test our understanding of the cosmological model.
Great, thanks. Any other questions from the audience? Nope. So if there are no more questions, this concludes the main part of the talk. If you have more questions, feel free to stay on the call and ask Collin. So I'm going to